let's look at the energy that goes into or comes out of putting solutes into solution. So the energetics of solution formation. Um, there are multiple things that happen. So we're gonna like slow this down and look at it tiny step by tiny step. So if I have, let's say I'm going to take sodium chloride, dissolve it in water. One of the things that I need to do at the very beginning is take my solid sodium chloride and separate it into the ions. So ionic compounds, they exist as their constituent ions. You split everything up. So I need to put in energy to split those up. And so this would be endothermic always. It will always be endothermic to take a solid and break it up into whatever pieces it needs to be in, whether that's individual ions or just taking the solid molecules and breaking them apart from each other. The other first thing, so steps 1 and 2 here, I mean, either one could technically be first, but you'll see why they're kind of in this order. The second step or the other first step is that I need to make space. So if I have just liquid water, all of those water molecules are interacting with each other, and they're interacting with each other through hydrogen bonding and dipole-dipole interactions, but they have hydrogen bonds, which are the strongest intermolecular force. I am going to have to break some of those so that I can move them apart. So there's a hole for this ion or molecule to go in. In my sodium chloride example, it's the ion, right? I need a hole to put my sodium plus in so that all of the negative parts of the water dipole can line up to surround it. So that's also always endothermic because I'm having to break up intermolecular forces in the solvent to make space. And then we mix it together. So the ions or molecules go into the spaces between the solvent molecules, and then the solvent molecules interact with the solute pieces. The mixed together part is always exothermic because I am creating interactions, like the intermolecular forces are forming. Now, if we bring back our good friend Hess's law, this means that overall, a delta H solution, so the change in enthalpy when I go from solvent and solute to solution, it's the sum of these 3 steps. So the first step, I have it labeled as delta H solute, always endothermic. That's where we break up the solute. Delta H solvent, that's where we break up the solvent and make space. Also always endothermic. And delta H of mixing is my always exothermic step. Now I've put the solvent and the mixing together, right? I specifically put the solvent second because the delta H of the solvent plus the delta H of mixing, we can combine and call that the delta H of hydration. So hydration is the process of making space in the solvent and then putting ions or molecules there. So those 2 steps together, that is the whole process of hydration. For an ionic compound, the enthalpy of hydration is always negative. So if we have an ionic compound, great. If we don't, we'll have other things that we have to consider. So now that this is combined, my delta H of solution, it's the delta H of the solute plus the delta H of hydration. Delta H of the solute is where you break bonds. Delta H of hydration is where you dissolve the pieces. So we've got one thing that is endothermic, breaking the bonds. If we have an ionic compound, we have something negative. We don't know how negative it is, and on occasion we will have something positive if it's not an ionic compound. We're going to generally think about it as the endothermic part and the exothermic part. So if these are pretty much equal to each other, so let's say that the delta H of solution is 0. So there's no endothermic versus exothermic um, reason for this to move forward. However, our favorable, not favorable, spontaneous, non-spontaneous, it's all delta G stuff, which also includes entropy. So you can have a delta H of solution approximately 0 and still have something go into solution because we're increasing the entropy. If the endothermic part is less than in magnitude, so I have absolute value of endothermic part less than absolute value of exothermic part, right? So if you get more energy out than you put in, your enthalpy of solution will be negative. And if you put in more than you get out, so your endothermic part has an absolute value bigger than your exothermic part, your enthalpy of solution will be positive. It'll be greater than 0. Now, that will either mean that it doesn't go into solution or that you can't be too positive. So if the enthalpy of solution is not too positive, we will still get we will still have things dissolve, but it will be purely driven by entropy. Okay, some examples, all of things that hopefully will be a little bit familiar to you. And at the very least, you can think about them in terms of the solubility rules. So sodium fluoride, this going into solution, so I have solid sodium fluoride turning into the aqueous ions. This has an enthalpy of solution of plus 0.91 kilojoules per mole. So overall endothermic, but just barely, right? This will go into solution. It's just going to be driven by entropy. I'm going to come back to potassium hydroxide, actually. Let's look at silver nitrate. So silver nitrate is soluble according to the solubility rules, and it has an enthalpy of solution of 36.91 kilojoules per mole. So it's quite a bit endothermic. But if it can get that energy from somewhere, I mean, let's say even we heat the solution up, plus the entropy increase that you're going to get from dissolving it, this will still dissolve. Potassium hydroxide, though, my middle one, this has an enthalpy of solution of negative 57.56 kilojoules per mole. So this is highly exothermic. This amount of heat being given off just by dissolving something in solution, remember that that heat is going somewhere. So if this reaction is exothermic, that heat is heating up the water that you're dissolving it in, which will make more able to dissolve, which will give off more heat. It just keeps, it can get really, really hot when you dissolve something like potassium hydroxide. And sodium hydroxide is the same. So this is one of my cautionary at-home chemistry warnings is that if you look at any kind of at-home soap making, it usually involves making a lye solution, which is dissolving sodium hydroxide into water. People have done things that range from melting a pitcher to catching their entire kitchen on fire because this dissolution is so exothermic.